So, all right, so our goal, again, just to recap, is to find the slope of this line that's tangent to this curve. We picked a 0.25 for no particular reason. We just had to pick one. And we know that it's increasing. We'd like to find its slope, but the problem is we have but 1 point, and we usually need 2. So what we're going to do is get the next best thing to a tangent slope. And that is we're going to find the slope of a secant line. You get a secant line by connecting 2 points on a curve. So I'm going to scroll down onto this next page here. And here I've just sort of zoomed in on like the first quadrant part of the graph. It's still the function y equals x squared plus 1. We're still interested in the 0.25. That's our point P. But now what we do is I'm going to pick some other point. I'll throw it up here. I'll call this a point Q. And now I'm not being particular about that point, right? It's some other point on the curve. So I'm just calling it XY. What I know is that the Y coordinate is x squared plus 1 because it's on the curve. So I could rewrite this as x comma x squared plus 1. And oops, we want that slope. Now that slope will get us pretty close to the tangent slope. It won't be perfect. If I pick this point Q and push it like kind of closer and closer to P, it'll get closer to that tangent slope. Right now though, let's just sort of come up with the expression that gives us the slope of that secant line. Now we have 2 points, so we'll just use our slope formula. So the slope of this line PQ, y2 minus y1 over x2 minus x1. Let's see, change in y. So x squared plus 1 minus 5 over x minus 2. And we could just simplify the top. We get x squared minus 4 over x minus 2. We know so regardless of what point I pick for Q, right? Regardless of which other point I pick, as long as it's not P, as long as I'm not picking the same point again, I can get the slope using this formula. If I try to pick P, I would be dividing by 0, right? But what I want to do is push Q closer and closer and closer to P. And the closer Q gets to P, I imagine Q is sort of like a free point that it can sort of just slide up and down the curve. The closer Q gets to P, the closer that secant slope is to the tangent slope. And so this process that we're describing by letting Q get closer and closer to P, that's a limit, right? And we spent some time evaluating limits before. The slope of the tangent line is going to be obtained, which I'm going to call just M tan, by taking the limit as, and I'm going to write it in a kind of an odd way right now, the limit as P approaches Q of the slope of the line connecting P and Q. And now this is the limit. We know the slope of the line connecting points P and Q is x squared minus 4 over x minus 2. Now if P is approaching Q, what does x approach?
Two.
Yeah, x has to be getting closer and closer to 2. And we know how to evaluate this limit, right? The idea behind evaluating a limit like this is to see if we can't do some algebra. The top will factor, x plus 2, x minus 2 over x minus 2, and we can cancel the x minus 2's. Now this is the limit as x approaches 2 of x plus 2, and we get a slope of 4. So the limit kind of allowed us to find the slope of a line when we only know 1 point, which is pretty cool. We're going to generalize this now. Here we started with a known point, right? We said we wanted to know what's going on at the point 2,5. And if I wanted to find the slope when x is 0, or when x is -2, or when x is 1, or whatever, I'd have to set up the limit again. We could actually find the slope at whatever point we want for a given curve, for some fixed curve, right, like x squared plus 1. We have the ability to evaluate this limit just once, and evaluate the limit once so that it gives us like a formula that will tell us what that slope is going to be at any point. And that's what we're looking at on the other page. So we have our fixed point x at x f of x, right? So imagine p is fixed, and then our free point is q. There's a little error in this figure here. This should say x plus h should be the x coordinate, and then f of x plus h for the y coordinate. What we're doing in this figure is saying, okay, we've fixed this point p, and then the way we're going to get that other point, the way that we're going to get this point q that's going to set up the secant slope, is we're just going to go up the x-axis by h units, right? Whatever that distance is, so that our new x coordinate is x plus h. And then, of course, the y coordinate is f of x plus h. So that's our point q here. And if I imagine q is this point that could slide on the curve up and down, and I want to push that closer and closer to the point p, now, instead of saying let's let x approach, some fixed point 2, what we're doing, if we push q closer and closer to p, what we're doing is we're shrinking this distance h to 0. And so the limit, or the slope of a tangent line at an arbitrary point on the curve will be given by this limit. The limit as h approaches 0. On top we have the difference in y's, f of x plus h minus f of x. And on the bottom we just have h, because this is the difference in x's, x plus h minus h. And of course that just, x plus h minus x. And that just simplifies to h. So what we're going to do is do some examples where we find the slope at an arbitrary point. The result of this will be an expression with x's, like a formula where we could just, once we have that, we could plug in whatever x coordinate we're interested in and get that tangent slope. This tangent slope is also referred to as an instantaneous rate of change of f of x with respect to x. Like if we find the slope of a secant line, and not a tangent line, but I actually have two different points, and found that slope, that'd be an average rate of change. Like here's how it changes over that interval. And when we shrink it down to just one particular instant, we call that an instantaneous rate of change. So we're going to do some examples. Let's find some limits. So we want to find an expression for the slope of a line tangent to the curve, y equals 4x minus x squared. This is our f of x at the arbitrary point xy, and then we're going to use our answer to calculate the slope when x is -1, when x is 2, and when x is 3. Now, we're going to evaluate that limit that we saw on the last page, and in order to do that, we need the expressions for f of x, which we have, that was given, and we need f of x plus h, and then we're going to subtract them. Basically, I'm going to do some side work, some algebra work on the side to figure out what we get for the numerator there. So our f of x function, 4x minus x squared. F of x plus h, well, f of x plus h is just what we get when we replace x with x plus h. So I have 4 parentheses x plus h minus x plus h in parentheses squared. And let's expand this, right? Let's multiply this all out. We could distribute the 4. I'm going to FOIL out the x plus h. That'll give us x squared plus 2xh plus h squared, and then distribute that negative. So this is f of x plus h. What I want to do now, I'm gonna scroll right back down to this, but coming up here just to look at this limit again. Now I want to subtract f of x, right? So that's our next step. Let's subtract f of x And if I'm subtracting f of x, I'm subtracting all of this function. I'm subtracting 4x minus x squared, which means I'm subtracting 4x, and I'm adding x squared. So I'm going to just kind of make a little parenthetical kind of aside here. So the negative of 4x minus x squared, negative 4x plus x squared. On the left, we have f of x plus h minus f of x. On the right, the 4x minus 4x, those cancel. I've got this 4h minus x squared plus x squared, those cancel. I got minus 2xh minus h squared. So this, I think, is all of the side algebra that we need to do. All of this is to get us ready to set up and evaluate this limit. So the tangent slope is the limit as h approaches 0. I always start these problems by writing out this limit formula fresh every time. I write it out fresh every time because I know that it's something that I need to know, and if I write it out fresh every time, then chances are pretty small that I won't know it when I need to know it on a quiz or a test. So there's that. This is the limit as h approaches 0 of, on top we have 4h minus 2xh minus h squared all over h. So here's the limit that we want to evaluate. Of course, the problem with this limit, and I think it's one we could have identified as soon as we kind of introduced this limit on the last page, is that I want the limit as h approaches 0, and I can't let h be 0 right now because it'll make me divide by 0. But you'll notice every term in the numerator has a factor of h, so let's factor it out. And when we do that, now we can cancel that common factor of h. So we want to evaluate the limit as h approaches 0 of 4 minus 2x minus h. Okay, now we can let h go to 0. Note that this is a limit as h goes to 0. X isn't doing anything, right? So I'm only going to see what happens when we let h go to 0. That, of course, just makes this term here disappear. Any term that has a factor of h will go to 0. So when we let h go to 0, we're left with the expression 4 minus 2x. This is the expression that gives us the slope of the tangent line at an arbitrary point. That was one thing they asked for. That was the first thing they asked for. And then they said, use your answer to calculate the slope of a tangent line when x is negative 1, when x is 2, and when x is 3. I don't have to compute any more limits. This one limit will do the job for me. So all I'm going to do now is evaluate this at each of these values of x. So when x is negative 1, m tan is 4 minus 2 times negative 1. So that is 6. When x is 2, we get 4 minus 2 times 2, or 0. And at x equals 3, our tangent slope is 4 minus 2 times 3, or negative 2. So this way of finding the tangent slope, by saying we're going to find it for an arbitrary point xy, is by far preferred to just picking a point and setting up a limit that's special that works only for that point. Because then if I want to keep figuring out what's going on with this function, I need to find a new limit every point I want to look at. And doing it this way only makes me have to compute this limit once. Now, before we do the next one, I want to just maybe ask a couple of questions to kind of prompt some thought about these results. So looking at these three values and the three slopes we found, where would I expect that the curve that it gave us 4x minus x squared, at which of these points do we think the curve is increasing?
-1.
And -1, and what tells you that?
Positive slope.
Positive slope. Where is it decreasing?
At 3.
At 3, right? Because we have a negative slope. What's going on when x is 2? Say that again?
It's the vertex.
Yeah, and if we describe the behavior of this parabola, it is a parabola, right? So we know that's where the vertex is going to be. But the behavior of the graph at the vertex is it kind of levels off. If we look at this graph, although I probably don't really need a calculator to graph it, but it will look something like. Let's see. It'll look something like this. Right, so the points we chose to look at were at like -1, 0, and 3, so right around there. If we evaluated the tangent slope at 0 or at 1 or 1.5, like any of these points over on this side, we would expect to get a positive result, right? And you can see that in fact will happen if you look at where is this m tan going to be a positive value, where is that m tan going to be a negative value. So right off, we could sort of see how the derivative can be used to help us describe the behavior of a function. And in fact, where does a function level off? Where do we have like peaks or valleys is one of the central like types of questions that we ask in calculus. Like there's a lot of application value to that, asking that kind of question. So let's do another one. We're going to find an expression for the slope of the line tangent to the curve y equals x cubed plus 2. So there's our f of x at the arbitrary point xy, and then we'll use it to find the slope when x is a half. Okay. So the first thing I'm going to do is just let's get an expression for f of x plus h. So it's x plus h cubed plus 2. Now you could take this and cube out x plus h, so you could find x plus h times x plus h, get that product, and then distribute and find, multiply by x plus h again. What we'll find is, because of how this limit appears, anytime we're evaluating this limit for some polynomial, it always involves raising x plus h, that binomial, to some integer power if we're working with polynomials. So I'm going to do a little bit of a side note here. I hope this will be valuable. So Pascal's triangle, we can construct ourselves, and here's how it works. It's like a little pyramid triangle thing. At the very top is a 1, and then the next row is a 1, 1. So far, pretty simple triangle. Each row begins with a 1. Then the next entries you get by adding the 2 above it. So this will be a 2. Every row ends with a 1. Each row begins with a 1. What should be the next entries in this row?
3. 1.
And what's the next row?
1, 4, 6, 4, 1.
And let's do one more.
4, 5, 7, 5.
We have another 10, right? Maybe I just didn't hear it, but there should be 2 10s here. And then we get a 5. And at the end, we have a 1. So we can, and Pascal's triangle can go on forever, right? Like there's no end point here, right? The numbers just keep getting bigger. So here's why we care about Pascal's triangle. I'm going to come back to that in a minute. But if we're evaluating, like for us, we're evaluating x plus h cubed. Now when you cube out an expression, you're always going to have your first term is going to be something times, and then you have all x's, so x cubed, x times x times x. Then you're going to have some other term where you have x squared times h, like h to the first. Then you'll have another term, x to the first times h squared. And then our last term, h cubed, all h's. Notice, okay, that if you add up the exponents in every single term, they add up to 3, right, which is what we were doing. We're cubing the x plus h. The only question is what numbers go, what are our coefficients? And that's where Pascal's triangle is helpful. We have 1, 3, 3, 1. So we're going to use that when we go back to the example, but I want to do just one more of these, okay? If I want x plus h to the 4th, I start out with all x's. So some coefficient on x to the 4th. My next term, the exponents, the powers on x kind of step down as the powers on h step up. So we're going to have an x cubed h. We're going to have an x squared h squared. We're going to have an x h cubed. And then finally an h to the 4th. And I write these exponents. You'll notice for every term, those exponents add up to a total of 4. What are the coefficients that we're going to write on these terms?
6, 4, 1.
Mm-hmm. So there's a lot of problems where you're going to be expanding, x plus h to some power. Let Pascal help you with that. Unless you just love like the distributive property and keeping track of all the terms. And I don't blame anybody for enjoying that. It's probably, somewhat therapeutic in some instances, but this can kind of cut down on some of the labor that you have to do. I'm going to go back to that example that we're at. So we have x plus h cubed. This is x cubed plus 3x squared h plus 3xh squared plus h cubed, and then plus 2. There's our f of x plus h. For this limit that we're going to evaluate, we have to subtract f of x. So we're going to subtract f of x. That means that we are subtracting x cubed and subtracting 2. Right? We're just subtracting each term in the f of x function. On the left side, we have f of x plus h minus f of x. On the right side, the x cubes are gone and the constant 2 is gone. So we are left with 3x squared h plus 3xh squared plus h cubed. Notice now when you're doing that, in the beginning we're focusing primarily on polynomials. So anytime it's just a polynomial that you're working with, by the time when you find f of x plus h minus f of x, every term should have an h in it. If I had a term that didn't have an h, like a constant term or a term with just x's, that would be a sign to me that I made an algebra mistake somewhere. If what you're working with is a polynomial, when you find f of x plus h minus f of x, every term's got an h. So going forward now, to find mtan, we're going to evaluate the limit as h approaches 0, f of x plus h minus f of x all over h oops, that's an x squared h in the beginning. Every term in the numerator has a factor of h, so we're going to factor it out. This is good news for us because this allows us to cancel that h. You know, when we first set up this limit, I mean, we should think of our first goal, intermediate goal, as being able to do enough algebra to get rid of that h on the bottom, right? I mean, we want the limit as h approaches 0, so a factor of h in the bottom is problematic for us. And now that we've done that, we can let h go to 0. What do we get? What is the result when we let h approach 0?
The only thing that's left is 3h squared.
Say that again?
The only thing that's left is 3h squared.
Yeah, that's the only thing left because the other two terms have a factor of h, and so when h goes to 0, those terms drop out. Here's the expression that'll give us the slope of a line tangent to the curve y equals x cubed plus 2 at an arbitrary point x. And the last thing they asked us to do was evaluate, find the slope when x is a half. So 3/4 is what we get. Questions on that example? Okay. All right. So look, if you really enjoyed this work that we've been doing on these last two examples, I've got some good news for you. So if we take a function, like some real valued function, this limit that we've been finding has a special name. It does, yes, give us a slope of a tangent line, but we call it the derivative of the function. So we're going to introduce some new notation. So we're finding the derivative of a function when we find the tangent slope. The process, like the verb form of finding a derivative, is not derive, it's differentiate. So this process is called differentiation. We have different notations that we use to talk about the derivative. One really common notation is the prime notation, where they just put this little tick mark on the f, so f prime of x, or y prime, as we see down here. That refers to the derivative. The other notation that is really common is this d dx notation, like dy dx or the d dx of f of x. And the reason we have both of these notations are really common. Both of them have their advantages to be used in certain situations over others. The reason we have two notations is because calculus was developed pretty much simultaneously and independently around the same time. Isaac Newton and Gottfried Leibniz in Germany. So the dy dx notation comes from the tangent slope concept, right? A slope is a change in y over a change in x, and if you, in sciences, that change, we use like a little delta to denote a change, so delta y over delta x, like a change in y over a change in x. And as you shrink those changes close to 0, we just abbreviate it as dy dx. You'll see both of these notations used a lot. In a lot of applications, I prefer the dy dx notation just because it helps me conceptualize the problem more. It kind of reminds me what the problem is about. But they're both used pretty widely. So the derivative of a function is another function. You know, when we find the derivative, or like in the last section we just said an expression that gives the slope of a line for an arbitrary point, what we're doing is we're finding another function, and that function describes your given function. So it sort of helps us describe the behavior. So let's find f prime of x. for this function, 2x squared plus 3x. It's the same problem, right? I mean, it's not a different problem. We're just using different language and notation around it. We're still going to find f of x plus h minus f of x. So f of x plus h, replace x with x plus h. I'm going to do some algebra to expand this. So there's our f of x plus h. We have to subtract f of x, which means we're going to subtract 2x squared and subtract 3x. As expected, we get these terms to cancel out. Everything that we're left with has a factor of h, which is a good sign for us. So I'm just going to go ahead and factor that h out now, and then we'll set up the limit. So f prime of x is the limit as h approaches 0, f of x plus h minus f of x all over h. We know what goes on top. Notice, by the way, kind of, I haven't made a point of talking about this, but I carry the lim. Right? Every step I have lim as h approaches 0, lim as h approaches 0. And we talked about that last time when we were just doing limits, how it's important to carry the lim through all of your steps until that moment when, in this case, we actually let h approach 0. This feels pretty good. We can cancel those h's. Now we want the limit as h approaches 0, 4x plus 2h plus 3. And so f prime of x, the derivative of f of x, if we let h go to 0, we're just left with 4x plus 3. And here it is. This is the function that describes how f of x changes. If I wanted to, or if they asked us to, we could use this derivative to find slope of a tangent line. So at this point, and as you do practice and answer questions, hopefully we'll begin to identify these two concepts: derivative of a function, slope of a line tangent to a curve, describing how a function changes. This is what the derivative does. So we've found derivatives now for a few functions, right? This one and a couple in the last section. And if our function is a polynomial, it goes the same each time, right? We're going to expand everything, we subtract f of x, everything will have an h, we factor it out, we let h go to 0, there's our derivative. We have to be a little bit more careful algebraically, maybe try some different techniques if our function is not a polynomial. So we're going to find the derivative of this function, y equals 3 over x plus 2, not a polynomial. Now we have x's in the denominator. So this y function, this is our f of x. So I'm going to find f of x plus h. The way we start is the same, right? We need an expression for f of x plus h minus f of x. So f of x plus h is 3 over x plus h plus 2. There's no expanding to do there. There's zero algebra for me to do with this fraction. That's f of x plus h. So now f of x plus h minus f of x is 3 over x plus h plus 2 minus 3 over x plus 2. There's nothing that cancels right now, right? Nothing cancels. There's no real low-hanging fruit right here where we automatically just sort of see a common factor of h. But we do have an algebraic path forward. I'm subtracting two fractions, and we know how to subtract fractions. What do we need? Say that louder.
Like the common denominator.
Yeah, we need a common denominator. And so we just have to remind ourselves that x plus 2 and x plus h plus 2 are completely different. They have no factors in common, right? I can't just do plus h on the last one. They're sort of, we could think of these denominators as being like relatively prime to each other. So what we're allowed to do when we get a common denominator is multiply the top and the bottom by the same thing. So we're going to multiply the top and the bottom of the first fraction by x plus 2. And the second fraction needs to grab an x plus h plus 2. Now we have a common denominator. So I'm just going to bring that common denominator down, x plus h plus 2 times x plus 2. Now, this is kind of important here, or I think it is. That denominator is written as a product. Leave it. Leave it. Like, there's no reason that you have to multiply out the denominator. You can if you really want to, but it really just creates more work with no actual benefit. Up top, we have 3 times x plus 2 minus 3 times x plus h plus 2. Now here, on top, we are going to multiply and expand out the top, because it isn't just a product, right? We're subtracting these two products, so in order to simplify, we're going to expand and see what like terms we have. Let's see, we end up with 3x plus 6, and then I'm going to distribute the 3 and the negative at the same time here. So we get minus 3x minus 3h minus 6. We get some nice canceling to happen in the numerator. We have a positive 3x and then a minus 3x here. We've got a plus 6 and then a minus 6. So the only thing we're left with on top is a negative 3h. And on the bottom, we have x plus h plus 2 times x plus 2. This is a pretty good spot for us to be in right now. So here's the simplified expression for the numerator of that limit. Let's go ahead and set up that limit. So dy dx is equal to the limit as h approaches 0, f of x plus h minus f of x all over h. So this fraction that we just found, that goes in the numerator of the fraction. All over h. So we have fractions within fractions, and I just made a little mistake here. Not an algebra mistake, but I left off the limit, so I want to make sure I include that. We have fractions within fractions, and so if I'm taking a fraction and dividing it by something, whether it's written as a fraction or not, I could think of this h as h over 1, I guess, if I want to. Dividing by h is the same as multiplying by 1 over h, so I'm going to rewrite this limit using that fact. And hopefully, if we weren't already pretty excited, hopefully right now we're getting a little excited, because what comes next?
There'll be an h on every term.
Say that again?
There'll be an h on every term.
Yeah, right? Like, we have a common factor of h. Now, here's an h divided by an h. Those cancel. It is at that point that we can really just declare victory. The rest of it is a fait accompli. Like, we're just about done. So what we're left with is negative 3 over x plus h plus 2 times x plus 2. You'll notice now, if you look at this limit, there is an h in the bottom, but that doesn't bother us because it's not a factor of h. It's not h times some stuff. H is just a term in one of the factors. So if we look at this term right here, as h approaches 0, x plus h plus 2 approaches x plus 2. So if we let h approach 0, the top is, now I'm not going to write the limit anymore because I'm letting h approach 0. I've got negative 3 on top. On the bottom, I've got x plus 2, x plus 2. Or negative 3 over x plus 2 squared. There's our dy dx. This is the function that describes how the given function y equals 3 over x plus 2 changes. The last thing they asked us to do is evaluate it at 1. So just a notation, a note on notation here. If I'm using the dy dx notation and I want to evaluate this at 1, we draw like a little vertical line, and at the bottom, like a subscript, we write x equals 1. And in fact, lots of sciences, this is really common. If you draw a little vertical line and then just state the value of a variable, it just means I'm going to evaluate it at this variable. This is the same as saying f prime of 1. So the f prime notation is like regular function notation. Just put in the number in the parentheses that you're going to evaluate it at. So we have negative 3 over 9, or negative 1/3. The derivative at 1 is negative 1/3, so if I wanted to, I could use that and interpret the behavior of the function at that value. I know that the function certainly is decreasing because its tangent slope is negative. It's not decreasing too steeply, it's because it's just negative 1/3. It's not like negative 5 or something, but decreasing nonetheless. Okay, questions on that one? So we know what to do if we have fractions, right? If we have x's in the denominator, this is our basic approach, is to, get your expression for f of x plus h minus f of x and get a common denominator. You're going to leave the denominator in its factored form. Like when we did the multiplying, we leave this factored. But multiply out the stuff on top. So now we're going to take, we're going to do another example. We're going to find the derivative of the function y equals the square root of x. All right, so that's our f of x function. So f of x plus h is the square root of x plus h. Nothing we can do, that's already simplified. So f of x plus h minus f of x is the square root of x plus h minus the square root of x. Nothing we could do with that. But there's no, we're not adding fractions, there's no common denominator. I can't get a common radicand if there isn't one already, right? So there's really no algebra for us to do. You know, we're not allowed to split up a radical over addition or subtraction or combine radicals under addition or subtraction. There's nothing for us to do with that expression by itself. So let's set up the limit and see what we're looking at. No h's to cancel. There's no common factor of h up top. And it almost feels like we're at a dead end with this limit. So what I'm going to do to kind of prompt us to sort of get us to buy into this next move, I'm going to open a new page, and I'm going to ask us to think back to when we were taking an algebra course or pre-calculus or whenever you looked at this. And suppose I was working with the fraction like 1 over the square root of 3. If I wanted to rationalize the denominator, what was our, like, does anybody remember how we could rationalize the denominator here?
4 times top and bottom by 20.
Yeah. Right, because on top we have root 3, and on the bottom we just have 3, right? So now I'm going to go a little further and say, what if what we were working with was not just root 3 on the bottom, but maybe like root 5 minus root 3. Now, if I just multiply by root 5, that doesn't get rid of all the radicals in the bottom. Same as if I multiply by just root 3, or even if I multiply by root 5 and root 3, it still won't get rid of all the radicals. But there's something we can pick to multiply by on the top and bottom that'll get rid of the radicals in the bottom. Does anybody know what it is?
Conjugate.
Say that again?
Multiply by the conjugate.
Yeah, the conjugate, right? The conjugate is what we get when we just change the operation in the middle. So we can multiply by root 5 plus root 3 on the top and the bottom. On the top, we just get root 5 plus root 3. On the bottom, this will give us 5 minus 3. You could FOIL the whole thing out and see for yourself, but basically you could think of this as how a difference of squares factors. If you have root 5 squared minus root 3 squared. So we have root 5 plus root 3 over 2. So that allows us to rationalize the denominator. So with this in mind, I'm going to go back to the notes, to this example. Our approach to evaluating or finding the derivative, evaluating this limit, is to now rationalize the numerator. So I'm going to take that same approach that we had in the last example, kind of extra example we looked at. I'm going to apply it here. I'm going to multiply the top and the bottom by the square root of x plus h plus the square root of x. On the bottom, again, I'm going to leave this like factored. I've got h times root x plus h plus root x. On top, I've got this product I need to evaluate. So if I FOIL this out, I have x plus h, because I have root x plus h times root x plus h, which is x plus h. For the outside product, I've got plus root x plus h. For the inside product, I've got minus root x plus h. And then last, minus root x times root x, which is just x. I just want to draw attention to an error I made. I talked about having root x plus h times root x plus h. That is, of course, just x plus h, not the square root of x plus h. So in the end, we have x. Now the outside product and inside product cancel. We've got x plus h minus x. So those x's cancel too, and we just have h on top. Hopefully we're all getting a little excited now, because we're going to cancel those h's. This is our goal, right? This is our intermediate goal when we set out to find this limit. I got to find a way to get these h's to cancel. So there we are. We're left with 1 on top. Now, in the bottom, there again, an h appears in the bottom, but it's not a factor of h, so I'm not worried about it. If h approaches 0, then root x plus h just approaches root x. So now let's let h approach 0. We've got 1 on top. On the bottom, root x plus root x, or 1 over 2 root x. And there's our derivative. There's dy dx. Questions on that one? Do we have another, what, 10 or 12 minutes? Okay. I think that's enough time to do one more example, and we'll be able to finish out this section. This isn't a new kind of function. It's just a function now that involves, like, it's got 2 terms. It's got, like, a polynomial term and this fraction term. We already have the tools and the techniques to deal with a limit like this. And there's more than one way you can approach the algebra to this, but I'm going to just sort of propose one way to go about this. We start off the same way. We need f of x plus h. So we're going to replace x with x plus h. Oh, that's a plus. Sorry. Plus 5 over x plus h. Now that polynomial part, we're going to do what we usually do with polynomials. We're going to expand it, right? So Pascal's triangle, right? If you use Pascal's triangle on this, you get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I'll distribute that 4. I said distribute the 4, and then I proceeded to not distribute the 4. Let me fix that. We want to subtract the original function. So that means that we're going to subtract 4x cubed and then subtract 5 over x. The 4x cubes actually cancel, right? That's the only thing that will cancel right now. We have these fractions on the end. If you look at those terms in the beginning, right, at the front of this expression that we got from the polynomial part, they all have an h, so I'm pretty psyched about that. It's the fraction parts on the end that don't have a common factor of h, but we know how to deal with fractions, and that was, let's just do the subtraction. Let's get a common denominator. Now, some people look at this problem and they say, I'm just going to get a common denominator for the whole thing, right, so I'll take the polynomial part and put it over 1, and you can do that. You're allowed. It'll work. I think it's more work. So I'm just going to kind of segregate out these last 2 pieces and add those fractions. So I'm going to do times x on the top and the bottom for the first fraction, and then times x plus h on the top and the bottom for the second fraction. Now, let's bring down these other terms. Now, so at the end I have common denominator, so I'm going to write that x times x plus h. On top we have 5x minus 5 times x plus h. I'm going to leave the denominator factored. I'm going to leave that denominator alone. I'm going to expand out the numerator. So now these 5x's cancel. I'm going to 5x and a minus 5x. And all I'm left with up here is a negative 5h, which means that fraction on the end has a common factor of h, right? Like, or has that factor of h that's in common with all the other terms in the beginning. So we should be feeling pretty good right about now. We want the derivative. We want dy dx. That is the limit. Again, I'm going to write it out fresh every time. The limit as h approaches 0, f of x plus h minus f of x all over h. We already just noticed that every term that we have here in f of x plus h minus f of x has a common factor of h. Let's factor it out. So what we're left with, when we take that h out from the expression, is 12x squared plus 12xh plus 4h squared plus negative 5 over x times x plus h. I think we all know it's coming right now. We're going to cancel these h's. And we want to evaluate the limit as h approaches 0. 12x squared plus 12xh plus 4h squared minus 5 over x times x plus h. Finally, we've reached the moment. We can declare victory. We are ready to let h approach 0. And when we do that, these things with a factor of h go to 0, right? The x plus h, as h approaches 0, just approaches x. So the expression that we're left with is 12x squared minus 5 over x squared, because I got two factors of x now in that denominator of that fraction. How's that? Questions on this example? Okay. All right. So I hope you like evaluating this limit over and over and over again. That's what you're going to kind of focus on in the exercises. Tomorrow we're going to look at, tomorrow's Thursday, yeah, so tomorrow we'll look at some, like how we think of how the derivative fits into different word problems, because the derivative describes how something changes, how a quantity changes. We're going to do evaluate more limits like this, and then kind of within some context. So have a go at the exercises. Let me know if you have any questions. We'll do some more of this tomorrow. And then I guess, oh wait, are we on break next week?
Yep.
Okay, great. So we'll do some more of this tomorrow, and then you'll be on break next week. All right, sweet. Thanks, everybody.
Thank you.